Hi, this is an addendum to the earlier talk on the sacred geometry. It's trying to provide some backup and context to a variety of the assertions that were made there. So having said that, let's go off to share screen. And what we see going on here, is we talked about a 26-dimensional space which had 10 dimensions for matter, 10 dimensions for dark matter, and something called a boson runs around in all 26 dimensions. So that's what we're going to come back to right now. So where did this come from? Where did this idea come from? In Western science in 1962, Richard Feynman, the Nobel laureate physicist, was at Caltech and gave a class on trying to include quantum effects into general relativity. And to do so, he started off postulating the existence of a particular type of field called a graviton. And the graviton, as such, would have spin. He started off with spin 0. It would always have to be in an integer valued number, 0, 1, 2, 3, etc. And he followed this through, trying to see if he could come up with a self-consistent theory for a spin 0 graviton that would include, therefore, the quantization of gravity. He showed that it was impossible to do this with a spin 0 graviton. He then tried to spin 1 graviton and had no luck. When he got to a spin 2 graviton, he saw that there was a chance to, in fact, develop a consistent quantum mechanical theory of gravitation there, but it wasn't clear what it was. So that was what the course was dealing with. You can find this on Amazon. The course notes are available. So that was in 1962. So now we go forward in time, and we come up with a different individual, Claude Lovelace. I'm going to pull this up. We'll see if this works. And this is an article. His obituary. He died in September 7th of 2012. But what in the world, why are we talking about Claude Lovelace? Well, one of the things that he did was he followed up with what Feynman was talking about in 1970, and he postulated that he had a bunch of vibrating oscillators. The oscillators were all generating bosons, spin 2 gravitons is what he was targeting. And that was how they were linked. Having done that, he discovered that he had all kinds of issues with having infinities, having particles traveling at faster than the speed of light. And he did something very original. He said, well, let's see if we increase the number of dimensions. So we increased the number of dimensions from 4, 3 for space and 1 for time, and he went up to 26. When he reached 26, all of a sudden, all of the issues he had with his particles being faster than the speed of light and having all kinds of infinite masses disappeared. So we had a 26-dimensional bosonic model. The boson, the simplest example of a boson, is the photon, and we'll come back to this in a second. So he was the one that came up with this, and he gave a number of talks on it. He wrote a paper on it, which you can find. Having said that, he was unsuccessful at getting anyone to pay attention to this. So that's where in part this came from. What I'm going to do now is just switch over to a little different view of things. Hold on a second. And what I'm dealing with here is what's called the standard model. The standard model is what was developed all throughout the 20th century till 1975, and it really hasn't advanced since 1975. So the standard model includes matter, which are called leptons and quarks. And so what we see for things that are leptons, we have the electron here, for example, as a lepton, but the electron actually has two other resonances, is what we'll call them, something called a muon and something called a tau. And these are all tied to the electron. And similarly for the neutrino, there's an electron neutrino, and then there's two others, the muon neutrino and the tau neutrino. So there's the pattern of three occurring here. And that's for the leptons. And then we have, for quarks, we have quarks, for example, this up quark has a charge of plus 2/3. The down quark has a charge of minus 1/3. And when we put these together, for example, we take two up quarks, so we have 2/3 plus 2/3 or 4/3 with one quark of a down quark of minus 1/3. We end up with 4/3 minus 1/3, or a charge of plus 1. That gives us a proton. When we take one up quark of charge 2/3 and two down quarks, each of minus 1/3, we get 2/3 minus 1/3 minus 1/3, or we get a neutron. So the neutron is made up of these two, the proton is made up of these two. And so it goes. So now let's simply go back here. I'm going to get out of this for a second and go back to our original picture that we had here. Here we go. So what we saw here in this picture was we had three holes in this 10-dimensional matter subspace out of the 26 real dimensions. The three holes themselves generate resonances. Two physicists, Witten and Strominger, showed that, for example, if there are three holes, then there have to be three resonances. Well, we just saw that the electron and the electron neutrino each have two resonances, which suggests that this might be a good match for what's going on with matter. When we go over here to dark matter, we end up with a different story. We have four holes here, and all we have here for dark matter are subquarks. If we go back to the pictures, the observations that were made, it isn't simply Ron Cowan that made these. Annie Besant and Charles Leadbeater made these observations in the 1894 to 1908 timeframe. Under deep meditation, they discovered that the basic, they called fundamental particle, which I'm calling a subquark, they called the universal physical atom, and it had 10 strings associated with it, and energy got resonated inside these 10 strings. So you think of the energy as kind of a jelly that's filling this up, and all these strings are vibrating like crazy. Another gentleman, a Mr. Babbitt, also in deep meditation in the 1880s, saw something quite similar to what Leadbeater and Besant saw here. And what Leadbeater and Besant saw is what Ron Cowan saw here. So for matter, we have this. What's different here, having two different types of whirls occurring here, some going in the positive direction, some in a negative direction. These are all pictures from observations of Ron Cowan. What he also saw for dark matter was that over here, dark matter, instead of having 10 strings, had 5 strings. And the vibrations that it generated, there was no charge, no notion of charge whatsoever. So we ended up with just these subquarks. and they clustered together into what he looked like a fern here. But as time went by, more and more of these things clustered together. And the thing to keep in mind is that this achieved sentience. There was a critical mass here, and that these achieved some notion of sentience, and that in fact he made observations here in his book. You'll see drawings in his book, The Path of Love, the Future of Buddhism as a Science, whereby there was a pictures of the 7 chakras that are associated with the 7 physical regions of your human body. And so each of these subquark conglomerations, which themselves have some sort of sentience, are apparently all 7 of them are linked together somehow through some sort of notion of etheric communication, and that gives us probably something that we would call a soul. So that's what we have here. Over here, the 4 holes should create 4 resonances. Ron didn't see anything here. That doesn't mean it's not there, it's just that we didn't look. Another thing that we noticed was we talked about space-time, and we had the 4 dimensions, x, y, z, and square root of -1, or I, times c, the speed of light, times t, time. Here, this gives us space-time. So when we looked at its dual space, the thing that's rotated 90 degrees away from it, multiplied by the square root of -1, we ended up with ix, iy, iz, and then minus ct. Notice that time here shows up, but it's minus, okay? So this suggests there might be some linkages here between what happens over here and what happens in dark matter and what happens with matter. And in particular, this might suggest how synchronicity occurs, that we have time going in the wrong direction. So this is left as an exercise to be worked out. We don't really understand this at this point. I asked also Ron to take a look at the curvature, and in mathematics, that's displayed as an array of 4 numbers called the Hodge diamond. He observed 3 different sets of curvature for matter, dark matter, and for this synchronizing Calabi-Yau manifold. And here they are. We have yet to do anything with that. It's clear that they're going to influence what's going on through the curvature, through the bending of these manifolds. We just don't know what it is at this point in time. So let's go back here to something. I'm just going to cut up here to this to try and summarize. Here we have what physics worked on for hundreds of years, coming up with these constituents, these quarks, and we saw these quarks are all made up of subquarks. There's 3 subquarks for each of these quarks here. That's what Ron Howard Cowan, that's what Annie Besant and Charles Leadbeater observed for all of these things here. And so we have things called leptons. Here, the lepton doesn't have any quarks to it. So the electron, as we saw, and the electron neutrino are fundamental, but there's 2 resonances associated with each of these because of the 3 holes here in this matter. Then over here, we have the bosons. We have the Higgs boson, which was actually experimentally measured in 2012. And that permeates everything. It's simply a scalar. There's no, it forces everything to have the masses that we expect all these different particles to have. If this were 0, then there wouldn't be any masses for any of these. And it was 0 at the bounce when the universe was created, but then it kicked in, it broke off, and that created the masses that we have throughout the entire universe. Now, here we've got three bosons, a photon, a Z boson, and a W boson. Here they are, and then we've got another one plugged in here with a gluon. Okay, it could very well be that the gluon doesn't exist. We'll leave it there for now. And the photon, in fact, has these other things as resonances, because again, there can be three resonances here. This is simply a conjecture trying to make things make sense. Okay, so that's for matter. Now we get into we try and extend this. The standard model has to also work for dark matter. So the first first of all, there's no electron, there's no notion of charge. So when we try and extend this over here, there's no electrons. There might be this notion of an electron neutrino over here, but then there'd be four of them. We don't know what happens here. And then similarly for the quarks that are here, they're made up of the subquarks. We don't know what's going on, because the key thing here is that for dark matter, there is no charge. Okay, there is no electron, and so just trying to be symmetric, we come up with these hypotheses. We would also look at how, when we have an actual space compartment here, how many dark matter subquarks can fit into a space compartment. Ron Cowan observed there might be at most 3 matter subquarks that would fit into a matter space compartment, the foam of space that's all around us. So there is some type of Pauli exclusion principle here, where you can only have something in one state occurring there in space, but we don't know what it is for dark matter for the space compartments there. And then that suggests, if we just wanted to naively jump into what the foundational equations would look like, then a standard approach is to use the Dirac equation, which are relativistically correct equations, and it results in the Schrödinger equation in the classical limit, and so forth. And this comes fine for matter. However, for bosons, we have a problem here, that all we can come up with, for example, is the photon, and we don't know what in the world is happening beyond that. This is all to be determined, and we would look to what Wolfram has been doing with using network graphs as a model for the quantum foam of space itself, a 26-dimensional hypergraph. So that's what we right now is working hypotheses, think is what's going on. And with that, we will wrap things up. All the best.